but also the cosmos as well. And he does lots of really cool statistical techniques, and he's pushing the envelope there in terms of geometric variational inference. And he works with really large surveys, and he's going to tell us all about the cool stuff that he does. And I'm sure it's great.
Thanks, Catherine. And thanks everyone for joining online as well as here. I just heard that this is usually a very open discussion format. That sounds great. Like, I'm very happy for interruptions, questions, discussions, also because it's sort of a mix of, well, being an amateur statistician, aka astronomer, and at the same time also being an amateur astronomer who spends too much time in statistics instead of doing actual work. So that's the theme of the talk, and therefore I'm happy for discussions and input and questions if anything comes up. Right, so for context, I want to talk about techniques that we use in order to make large-scale reconstructions of the cosmos, or in this case, the Milky Way. This is just as an example to get a bit of a feeling for what are the problems that we try to solve. This is the 3D distribution of dust in the interstellar medium within the first few kiloparsecs around us. And we have a lot of tomographic data in that volume, and we want to essentially reconstruct, in this particular case, how does the 3D distribution looks like. And basically every single point in that space, every single voxel in that volume, we consider an unknown degree of freedom. We want to recover all of them from observational data that we have on it. So that's the sort of Bayesian theme and Bayesian setting for these type of problems. And to put this a bit more into abstract context, the main reason why we do this is we want to, at the end of the day, answer questions. Yes.
So can you say something about the data that's in there?
Yeah, of course. So the data in this one is basically tomographic information coming from line of sight integrals to stars. So there are many stars in that volume, and we think we know how bright the star should be, and then we observe how bright it actually is. And the amount of absorption gives us, for each star, tomographic tracer of that structure.
So the gaps that you see are really gaps in the sense that it's low density.
Yes, there are roughly 60 million stars in that volume. So if something is empty, it's really empty.
And this is from Gaia.
Yes, this is Gaia XP. Right, so to put this a bit in an abstract framework, the main reason why we do this, or one of the main reasons, is we want to answer questions about the system that we care for. And we want to answer questions being Bayesian in a Bayesian setting. So we essentially care for trying to get probabilistic estimators for questions that we want to ask. And we do this by defining a signal, defining a model for the thing that we look at. In this case, let's say the 3D density of dust in the Milky Way. And then we, given data and a model relating that signal to the data, as well as understanding the measurement process and understanding the nuisance processes in this forward modeling fashion, we can recover what's the distribution of signals given the data and this model assumptions, and from there answer all the questions that we might want to pose. So that's sort of the Bayesian framing. And one more addition to sort of standard just base that we like to do is we like to standardize our prior, meaning that if we have a generic prior model for the signal that we study, we reparameterize everything in a coordinate system where the prior takes a standard normal distribution a priori. That's mathematically doesn't change the problem. You're just labeling points in space. But once we come to numerical approximations, that's a much more useful coordinate system to start from.
What is N in your graph?
N for me stands for all the random variables that I don't care for, like all the nuisance processes.
Okay.
That I've marginalized over to get the likelihood. Yeah, I didn't write that out.
So you're going to a space where the prior is a unit normal. but-
Yeah.
So if there were a linear transformation that gets through that space, I'm fine with that, but it's non-linear, right? Or-
It's in general nonlinear.
Yeah.
Yeah.
So. It seems like there's lots of places you could go wrong in choosing that. Because first of all, there's infinitely many transformations you could choose.
If you keep the parameter, the number of parameters the same, then up to like unitary local rotations, it's unique. So you
Okay.
cannot go wrong in that sense. You can only stay within one equivalence class.
Okay, so it is unique up to rotation.
But local rotations, so it's like, there's quite a lot of degree of, like.
Yeah.
Yeah. Any rotation in this high dimensional unit Gaussian space will give you a unit Gaussian. That's kind of the symmetry.
Okay,
Yeah,
But is it guaranteed to exist?
if the probability is proper, if the prior probability is proper, it's guaranteed to exist, yes. And that's where I become where I draw the astronomer's card and be like, improper priors, I don't know how to do this, it's too complicated for me. I will cut away all the space that is probability 0 and then redefine as proper. To put it that way. Right, maybe a bit more visual when I talk about these generative models that generate signals. For things like the dust map and other tasks, one very common process that we use a lot is a Gaussian process or Gaussian process-based priors. So basically recipes that turn random numbers into correlated random functions or discretizations of those across the domain. So give a bit of an example. This is kind of a scheme of a two-stage generative process where we first generate random function that tells us how correlated things are. This is a very typical, astronomers like to think in power spectra. So we first generate a power spectrum and then conditional to one power spectrum, we can generate a random realization. And then the joint set of numbers that define a power spectrum and the random numbers that draw the realization, these are then the parameters that we care for and that we model the system with. And then of all the possible functions that you can make up with that, which is like not any function in this 2D space, but any function that sort of falls within that prior volume. The sort of inference task is to figure out the one that's consistent with the data. And this is an example application where we've taken basically the approach process that you just saw, just with one more dimension, because this is space and time. And then as given the EHT data on M87, how would the space-time posterior distribution look like that's consistent? So of all the random functions, which are the subset of functions that are consistent with the data? That's like a set of samples to give you an idea. And so this is the problem space that we try to solve for, and there's a lot that could be talked about modeling and instruments and so on, but for today I want to focus on the other part, assuming that we know how to forward model. How can we find within the space of all these possible functions, how can we find the subset of things? And also to put a bit more of a perspective, like what do these problems actually have in common? Because from a astrophysics perspective, they are totally different. Yet we're using the same techniques to solve all of them. Changing the model depending on the problem, like here we have integrals for volumes. Here we look at Fourier transforms of images. Here we look at Fourier transforms at certain moments in time.
So I have a question.
Yeah.
To the previous slide. Where
Yes.
Generated M87 images. So all the images on the right are generated with your Gaussian model.
Yeah, these are posterior samples. So
Yeah,
this-
no, but it all comes from just the Gaussian generation.
But
It's the one which you it's not simulation from the.
no. No, this is the Gaussian prior, but combined with the actual data. Like, this is really, that's where the constraint.
Oh, because that's nice, it's different than what, and like you
Yeah.
said, the machine results were showing, where they actually had the physical model which generated the different shapes and images. So this is your,
Yeah, there's one sub-team in the EHC group that does forms of regularized maximum likelihood, which I would say in spirit are similar modulo the uncertainty quantification. And now I think there's also a newer version where they do full posterior sampling
okay.
on like low resolution image space as well. So I think things have changed since then, but yeah, absolutely.
So that's interesting, yeah. This-
Well, but it took us a long time to convince everyone that this is actually fine to do back then. Now
Yeah.
things have been much more accepted. That's great. Yes, so I think that the general theme that prevails is we kind of have two, from an abstract perspective, two problems simultaneously to solve here, which are both annoying, which is on the one hand, these problems tend to be very large. I just mentioned 50 million stars in that volume, and we use 500 million voxels to represent the function. Maybe we can do better than that, and there's a lot of empty space, but that's on the modeling side. But nevertheless, you have that much data, and if you have this big of a volume to fill, it's a big problem to solve. But at the same time, uncertainties remain large enough that you still care for them. So if you were to ignore them, and if you just try to make a point estimate of that, it will look much worse. Because distances to stars are uncertain, and really uncertain that you just won't get the same fidelity. And in interferometry, it's a little different. There's mostly the instrument itself, the calibration part that makes this more tedious and makes this much more sort of structured as a problem. But again, with and without uncertainty quantification, the images do visually change. So one hand, big data problem. On the other hand, we do care for base, and it makes things better. Right. So coming back to what is the main thing that we want to do when we say we want to solve things with their base, or we want to have posteriors? For the most part, not always. There are also other questions we might want to answer, but for the prime part, what we care for is posterior expectation models. We want to be able to integrate over our posterior over functions. We want to know moments. We want to derive some downstream quantities that relate to the things that we reconstructed. So that is the main sort of challenge for us. And I just said that this is something we don't really want to do, but it's still something that comes to mind as the first thing to do. Let's just replace all that integral with its maximum density point. And this is usually a place where I would, depending on the audience, spend a lot of time. And I think here in the audience, I don't have to spend much time on this. If you try to do this in very high dimensions, this is not a really, really good approximation. It's actually a really bad approximation, because while this point has maximum density, it is far from maximum probability, because probability is density times volume, and in million dimensions, all the volume is out here and not in the center.
A quick question.
Yeah.
When is a high dimension? You mean you can see high dimension, not F, right? F
Yes.
is one dimension.
F could also be high dimension.
How high are we?
So,
talking about?
500 million or
That's
million.
reasonable high.
Yeah.
You think we're thinking about trillion, so.
Yes.
But, so I guess then it's rule out, but what's the dimension of a cassette? Sorry, I've been late here.
Yeah, dimension of T is similar. So, for example, for the dust map, it's every voxel is 1 degree of freedom in the problem. Now well, okay, this is the number of parameters in C. The number of relevant degrees of freedom is a different story, but it's still in the tens of millions, as in.
Okay. If F is such high dimension, cassette is such high dimension, and then why you're interested in the posterior mean, not the posterior mode, or any other posterior distribution of the efficacy itself?
I'm interested in the posterior mean of F.
That's
Yeah.
what you wrote there, right?
Yes,
Why that's the only quantity of interest? Do you have the whole posterior?
because I have not specified F yet, so we mostly, because it's posterior so high dimensional, we usually look at summary statistics and quantify things in terms of summary statistics. So I look at the mean and the covariance of the function I'm interested in. So F here stands for me to all the downstream physics questions I want to answer to
I
the
see.
system.
So it will be autocovariance area. Okay,
Yeah.
got it. It's not an F, it's a fixed one.
Yes,
Right.
yeah.
Got it, thank you.
Yeah, I was being a bit, it's not a fixed F, it's,
Yeah, and just to be clear, we don't just keep one dust map, we have samples from the distribution of dust maps that are consistent.
yes. And so, given the dimensionality of the problem and the sort of insufficient quality of point estimates, the next sort of cheap extension is, well, maybe I can replace the integral over the posterior density that I cannot calculate with an integral over a different function that I can calculate, and then just use that instead. So that's sounds very sloppy and hand wavy, and I can't just replace a function with another. But this is sort of the spirit. Well, unless you choose a good function.
Well,
And
in that case.
well, in that case, in spirits, this is kind of the theme that I want to talk about, different ways of doing variational approximation in that space. And here's an example with a Gaussian, which is in this case not really great choice, but it's better than no choice as a reference, and even in millions of dimensions, approximating things with a Gaussian that has a full covariance turns out to be not that easy, and going beyond that is also challenging. And so, yeah, that's the theme I want to talk about. Just quick reference to put everyone on the same page. We formulate the problem in terms of minimizing the variational part of the KL, which we choose for convenience because it has the integral over the thing that we can compute integrals over instead of the thing that we want to compute integrals over. And then formulate the problem in terms of a family of approximate distributions, and then choose out of that family the one member that minimizes the forward KL, which is also a lower bound to the evidence, depending on which side you start calculating from. And that gave rise, something we've worked on in the past, to two algorithms, one called metric Gaussian variational inference and one.
Question.
Yes, sorry.
You calculate KL distance from this Q sigma.
Yeah.
Which you know exactly,
Yeah.
and P, which you don't know. Right?
Yes. Oh, sorry. I don't know P, but I can evaluate its unnormalized density. So I do have an expression to evaluate it. I just don't know how to compute integrals over it. So, yeah, I work on.
This is so you can do the marginalized.
Exactly, yes. Yeah, sorry, when I say I don't know P, I meant I don't know how to integrate it. I do have an expression for its density, and that's very important.
But do you have sample from it? If you have,
No,
you don't have sample.
No. I have a functional form, we compute gradients and stuff, and that's what we're going to use for the most part. Right, so these are the two ideas I want to talk about, approximating with Gaussians, and then a way to go beyond that for unimodal distributions that use the same tricks. And just starting that theme again, we don't want to do this in 2, but millions of dimensions. So the number of parameters that we use to describe our approximate distributions, they are really costly to us. So we cannot afford many. In fact, we usually can't afford more than the number of parameters we have in our problem. So if you, and which is a strong constraint. If you want to model the distribution over something, you can only use as many numbers as the something that's or in that same cardinality. It's hard. And so instead, what we try to do is we try to make use of the fact that we can evaluate our posterior and its net negative log. And we can evaluate it and we can compute gradients of it, and we can try to make use of the fact that we have a functional form as much as possible. That's kind of the idea and the theme. And so what we want to do is we want to take that log posterior, and we want to, instead of parametrizing a family of distributions, we want to find a family of coordinate transformations that brings that into a space where things look simpler again. So, and in order to do that, in order to define coordinate transformations, we need a coordinate system. And so we start by looking at proxies for curvatures of that landscape. So one pretty well-known one is the Fisher metric, which is the expected curvature of the likelihood. And then if you recall that we are in this coordinate system where the prior is a standard Gaussian and its curvature is just the identity. So if you sort of want to look at the expected curvature of this thing, it's just going to be this this quantity. And to give a bit of a visual aid, that's kind of what it looks like. It tells you how curved your posterior, log posterior is locally at each point. And that's useful. So now we have sort of an idea of orientation and curvature. And now the theme is we could try to undo this change in curvature. And that would bring us hopefully into a space where there's less change in curvature as we just undid it. So basically, if I were to interpret this as a metric of a manifold, and then say, what if I walk along geodesics starting at this point and then go to this point and ask again, how do they look like? They will cover this entire density and give us an idea of a coordinate system which tracks the change in curvature of the log landscape. And now we have a coordinate system. Now we can ask, how do things look like in that coordinate system? And they tend to look simpler. A lot of the, especially these like funnels, which are annoying for many numerical tasks, they become much simpler and much less pronounced in this space.
So is there a way to physically understand where the funnels come from?
Where the funnels come from? So this is a very typical scenario that appears when you try to learn the mean and the variance of one thing simultaneously. So if this is kind of the variance and this is the mean, and there's also correlations between mean and variance in this case, then either you have very low variance, in which case the mean has to be a very particular number, or if the variance is larger, the mean could be more spread out. And when we, for example, when we have an electron density and a magnetic field, and we multiply them together, then how well we know the magnetic field from a measurement of the product depends on how strong the electron density is. So kind of these pictures arise all the time when we forward model physics. So we multiply and sum two things together and then measure the outcome. Yeah, that's the thing I take as an interpretation.
So finding this transform seems easy enough in 2 dimensions, but you can do this in millions of dimensions?
Yes.
That just sounds expensive.
That just sounds expensive. And important point is, this is where modern machine learning comes in handy. If you have an expression for your log density, you have automatic differentiation, you can compute its gradients, you can compute its curvature. If you can do this one analytically, you can even directly get the Fisher metric. If you don't, you can find numerical proxies for that. So the moment you have gradients and curvatures available of that function, getting this transformation actually becomes relatively simple. I will show the form in a second. Just let me conclude sort of the variational idea that we say is, okay, in that space, which is where things don't look exactly Gaussian, but they look closer to a Gaussian, this is where we sort of chop off and say, this is good enough for us. We will approximate things with a unit Gaussian here. draw samples from that Gaussian, and then use the inverse coordinate transformation to get approximate samples from that density. So,
One question I have is since it's of such high dimension, the origin posterior.
yeah,
If you're gonna using Gaussian, you roughly have some kind of assuming the other thing is unimode or close to unimode. Is that a reasonable assumption in such a high dimension?
yes, so that is a limitation of that approach. It turns out to be a reasonable choice for most of the tasks that we've looked at. But I cannot give a theoretical guarantee as to why this is the case. I do think that my intuition to why things seem to be unimodal, and the way we get confidence in this is, which is also no guarantee, is we run this analysis with random starting points many times and see if the modes that we end up in, if there's only mode that we end up in. Now,
That could be indicating a unimode, it could be just your algorithm stuck, never
Yes.
go anywhere. You don't really know which is which. The reason I'm saying this is that, we have been working on these high dimension multi-modes. And, the one idea you can still do the Q is do the mixture of normal, right?
Yeah.
Do lots of mixture of normal. But then you actually have a map, we just have a paper is about to finish that. I could just put on archive. You can map all these mixture modes into a unimode, there is
Yes.
a map, and it can undo it.
yes,
So this way you can go back and forth.
Yeah.
Now, although we only try to about solid dimension, and after that, it start things falling apart. So probably not there yet, but you have 500 million dimension, I just want to mention.
no, this is absolutely something where, there are two things that I sort of, think where we have to do better is, getting multimodality into this. This is a very unimodal thing, and the construction principle for the coordinate system really bases off of the variational mode that you end up in, where you start, and where you start depends on where you randomly start. So, but we do find things to be very consistent with totally random initial starting points in things like the dust map. And I think the reason for that is that we have so many more degrees of freedom than we have measurements. And I think this sort of, while there are weird funnels, I think our modes tend to be connected because we over-parameterize these problems.
So in a way, the problem is not really that high dimension. In terms of the signature you can actually discover, right? Because in these very high dimensions, it's very hard to have unimode, because all the masses scatter around, unless you have really, really strong signals.
Yeah, although, well, the signal is definitely on a submanifold, but then the submanifold, I think, is still very high dimensional. So that's where sort of the question lies. It's just very hard to visualize. And I'm also not super happy with the fact that the best we can do at the moment is try many times and see if it's consistent. Because that only tells you whether a mode is large relative to your prior volume, which you usually randomly start from. And a mode could be small relative to your prior volume, but still important in the posterior. That's
But also an ability to dimension space, if you try 1,000 times, okay, you checked out this
yeah.
1,000-dimensional manifold,
Yeah.
like 0% of the space, right?
No, absolutely. It's
But you're not alone, that's called a machine learning approach.
Yeah. I know.
Not a criticism.
No, I don't take it as a criticism. I'd be happy if someone hands me something that can deal with that, and then I can.
No, it's a hard problem.
It's a hard problem, yeah. Yeah. But yes, to conclude with the formal construction, so actually solving a geodesic equation, like following these points exactly, is expensive. But there exists pretty good local approximations, which are mathematically, it's a set of Riemann normal coordinates. So these are coordinate systems where I go to a point, I look at the metric of that point, and I also look at the curvature of the metric, so all the Christoffel symbols, and they also vanish. And that's kind of like one step better than a linear coordinate system where only the metric vanishes at this point. Now also its derivative vanishes. It's not the full geodesic, but this is what we use in practice, and they tend to do very well for us in practice. And then constructing that map, at least in the forward direction, is for us relatively cheap because it involves basically doing our forward model, going into a likelihood space, and having back propagation. And by doing this once, you end up in a space which is linearly related to all the other points. So that way is very cheap. It's on the same, it's like one model and one gradient call and you're there. For sampling, you have to do the inverse, so that's harder than we do this iteratively.
But when you say you're searching for the geodesic the past, do you go segment by segment? Like you gradually,
No, we actually use this as our global approximation.
okay,
And then we find the expansion point becomes our variational parameter. Then we try to find the expansion point for this approximation that is optimal in the variational sense. So that's,
you're trying to find expansion point.
yeah,
I
but I keep the transformation global. As in this is my approximation to transformation. And now I just want to find that point where this is where the corresponding distribution is best in the variational sense. Yeah,
I understand, but why only choosing one expansion point?
because it's cheap.
Right, but if it's cheaper once, probably cheaper twice, a few times might be
Yes,
give a little bit more coverage.
I have run a few experiments with multiple points and they were like their amortized performance was not.
Oh, I see, oh, taking time to
like,
speed, okay,
Yeah,
okay.
What does it mean to have multiple expansion points?
Well, because then you have a more flexible approximation, right? Because this is the parameter for approximation, that you can point. Essentially, your variation of that base is more flexible, has a better chance fits the original.
yeah,
Oh, you mean
Function.
difference? It's a vector, right?
yeah, exactly. So
So it's already multiplied now.
No, this is like
But it-
Newton expansion, right? Where do you
Yeah.
expand?
it's like one point in this high dimensional space
Right.
around which I expand the geodesic equation to solve for the coordinate system.
Okay.
And I could choose a different point, which would give me a different coordinate system, and I could ask, what is sort of their weighted average, or what if I go in segments?
Would it give you a different point?
It would give you a slightly different coordinate system, yes.
It will. Because it's a localized, right? Essentially, you're doing a
It's
localized.
a local approximation to
But
the,
it's supposed to be a smooth density, right? So it
Yes.
shouldn't change that much.
yeah,
This-
so,
This is essentially quadratic. This is essentially like a quadratic approximation.
yes, it's accurate quadratic. It does take into account higher order terms. We just, after the second order, we start losing some of the.
Yes,
Some,
yes.
yeah.
Yes, yes.
But the point is, the image you saw was done with that local approximation, and it was doing fairly well. So this was also sort of our, so all we can improve of is basically getting that shape closer to a Gaussian, which would help in high dimensions. It's very hard to say it's like good or bad. But I think it's also already doing a pretty good job, as the main issue that we have is the alternative for us before that was draw a Gaussian in this space, and this is certainly not worse.
That's clearly. But is it reasonable to assume that kind of the problems we've tried this on are somewhat convex, and if they had arbitrarily complicated landscapes,
Yes.
like it probably wouldn't work.
Absolutely, so convexity in the change in curvature along the typical set, that is like the dominant source of error of this approximation comes when you have like a change in orientation along a typical set. So let's say this bends like this and then starts bending like this, but the entire typical set covers that. Then you start to lose things.
Okay.
And you start to do worse with that, yeah. And this is where we could improve with higher orders.
But your point is well taken. This is much better than doing nothing.
But I agree,
Just call it
it's
better.
also very much not the end of the road, and I think
Yeah.
there's more to be done here. Than this, for sure. Just for completeness, because I've spoken about the Gaussian approximation that we do as well. This is a very small change in this equation. Instead of taking the full forward mapping in this part here, we again, if you also take its linearized version here, so now we have a linear coordinate transformation instead of a nonlinear one between psi and y. This is a linear set, which is much easier to solve. So the inverse is just a linear equation to solve. And that's sort of the metric version of the Gaussian approximation that has this kind of metric as a proxy for the curvature, because this is sort of the you're trying to find the best linear coordinate system that you can squeeze in there. And that's the only difference between this Gaussian and non-Gaussian approximations that I was showing. And then the very last bit before we conclude with the technical part. Again, this has nothing to do with mathematical improvement and reducing errors. This is just computational speed and performance. The change in the curvature of the coordinate system tends to be, especially in the beginning, not as important as just going down the hill and falling into a mode. So we do iterate between keeping the shape of the posterior static and just moving the point cloud. So basically just moving their relative position and updating the expansion point. So we kind of go in this, we move here, now we move to a regime where the shape of the approximation that we have doesn't really match anymore the target distribution. So now we regenerate samples according to this new expansion point. And we start moving that. And by iterating over this, we just get much faster convergence because we don't need to invert our coordinate mapping every time we move somewhere. Yeah, there's a turning point towards the end where things start to become more efficient to do this update all the time, and that's when we start switching. And also don't resample from scratch. So that's also very important. At some point, you can update your old samples instead of redoing.
Well, what's setting, like, essentially the resolution in this coordinate system? Like, how finely are you getting this?
In this coordinate system,
Yeah,
or
in other words, is it a one for one that you have one voxel with information and you're using every one, or is there some equivalent of smoothing or sampling?
so in the space of posteriors, we sort of have floating point precision resolution.
Right.
In the space of the functions or the dust map,
Right, when you actually use this, yeah.
yeah, there the resolution is the resolution in the dust map is fixed by what we defined in the
Yeah, I
beginning.
know that. I'm sort of saying, like, is this analytic enough that it doesn't matter what the resolution is? Or is there some level at which you're approximating?
Yes, yes. We work under the assumption that we've resolved enough to be in the continuum limit. As in, this is a sufficiently accurate resolution that that it doesn't change to the continuum anymore. The main point is to have resolution sufficiently below the uncertainties that you can recover. Because we're kind of in this space where if you think of some correlated Gaussian random fields and it has a falling power spectrum, but you can only learn until like this level of power that gives you a characteristic scale beyond, you don't learn anything. And whether you throw in more independent random numbers there and carry them along or not, doesn't change the outcome. Yeah.
Yeah.
The problem is you don't know that cutoff before doing your reconstructions, because how good you can learn things depends on the environment. And in the simplest case of imaging, where I have measurements everywhere, I can work this out analytically in practice. For example, Gordian's Edenhofer's dust map, the one I was showing, started out at one resolution and then went to a higher resolution on the way and sort of showed that things remain consistent and then said that's where we stop. But one could also do this iteratively. Okay, that sort of gives this family or this two ways of approximating probabilities, which are very much related. One is sort of the nonlinear next order extension of the other. Both have been very instrumental for us to going from well, before that we were doing point estimates, and point estimates just don't work in these problems. It was really and that was really the for us a game changer to go to this Gaussian, which has as many parameters as the actual problem, but still takes care of a form of correlations in all of that space. And then going beyond that was yet again helpful and instrumental for doing multiple components at once, like electron densities and magnetic fields. Like if you have one measurement of two things combined together, then you always get these funnels. And so Gaussian approximations don't work anymore. Right. And with this, let me go through a few examples. Maybe start with this to get a bit of a schematic one. This is kind of a 1D example. It's our toy example that's in concept related to things that we do very often. We have a nonlinear, in this case, log normal Gaussian random, log normal random field that we want to recover from noisy measurements. The measurements are assumed to be Gaussian, but the noise level is something we don't know a priori. We don't know how noisy things are. And we do expect things to be correlated, but we also don't know its power spectrum, so we don't know exactly how correlated things are. So the task is sort of from all these points, recover the function as well as their sort of prior and likelihood statistical properties within that model. And that's a very common task, and there we can benchmark sort of how good or bad we are. And the spoiler is, well, both methods, this is doing GeoVI, this is doing the linear version. They both do a good job at the actual function representation. They look pretty similar. But once you go to the higher order statistics that describe then the uncertainties, there things start to matter, whether you do a Gaussian or non-Gaussian approximation. And for reference, here we can also do ground truth as in Hamiltonian Monte Carlo sampling. And this is yet again, especially when you look at like power spectrum, also the noise estimation distribution. Again, this is GeoVI and this is HMC. So also there, the more sort of high level nonlinear related the quantities are to the things that you measure, you always lose something in this kind of approximation. So that's the rough scheme. For the rest of the talk, I mostly want to show some astro examples and give a bit of context.
So
Yeah.
didn't quite get what's the data from?
Oh, this is artificial data. Yeah.
Where does it come from? I mean, how do we generate?
Oh, self-consistent with the model that we're working on here. So I have a statistical model for the functions, which is a log normal process. And I draw self-consistently and then I draw artificial measurement.
Oh,
So-
so you just, okay, so you just have it.
Yeah, I only want to compare the approximation capabilities of the different samplers.
I mean, it's not, I mean, I was wondering if you're doing karma or ARMA or those.
No, this is all,
Just simple sampling.
Yeah.
One by.
right. Yeah, basically very similar example. I already mentioned it in words, but just now in pictures as well. The task of recovering the components of the so-called Faraday sky, which is a measure for us tracing the magnetic field of the galaxy through the lens of electron densities seen as, or the line of sight integral of electron densities seen as the dispersion measure, is something if we think of this funnel-like problem, if we want to recover the magnetic field and we see it through that lens and we don't really know how this looks like, we kind of get this problem that in some places we have very high signal to noise on that map, and in some places we have very low, but the relation between the two is this nonlinear multiplicative one. So if you have only noisy data on both of them, and this is where we basically get noisy data on the product of the two, and then some very sparse data on this one. And then in this example, we have a third component for which we also have noisy data, which is basically tracing the electron density squared integrated along the line of sight, the emission measure. And so you have these tracers that are all related to each other and not the most complicated way, but at least in a linear way. and you want to simultaneously recover them. So this is where we have reason to believe that things are unimodal enough. But we do have these funnel-like degeneracies coming from the fact that if I make one component stronger, another component has to be more or less confined. That's the sort of geometric interpretation. And so particular, this analysis was one of the first sort of astroanalysis where we went from the Gaussian to the non-Gaussian one and really saw that it made a significant difference where the Gaussian one just wouldn't work anymore. But you can also do a lot with the Gaussian one. The dust map that you've seen, this was done with the Gaussian approximation, this version of it, which already gives you pretty good result in this case because there are so many stars, and while the uncertainties matter, they don't become extremely nonlinear. But this is sort of to give you the theme for, on the one hand, you have a lot of measurement. Imagine 50 million of these blue dots here being your tomographic information. But nevertheless, uncertainties matter, as in this is flipping through the posterior samples. And for one, things get worse when you go further out because distance uncertainties get worse. But there are also some non-trivial things, as like, here's a very dense dust cloud, and how well we can see stars depends on how much dust is in front between the star and us. So if there's a very dense dust cloud, we see a lot less stars behind it, and hence we have a lot more uncertainty behind it. But we don't really know where this dust cloud is beforehand. And so the fact that this one is very well constrained in structure and distance, and this one isn't so much, is something that's very hard to tease out if we do everything sort of by hand. And this is where this comes in handy, that we can probe the uncertainties even in this high dimensional space.
Following up on
Yeah.
Alisa's question about scales. So to get this, you got to do interpolations between.
Right?
You had to do interpolations along
Along the,
directions.
yeah.
That, suppose you got to start one point, another one offset from somewhere. You got to get to get the estimates of the dust in between. You got to do some sort of interpolation.
yes.
And then, how do you, so especially when you got a dust cloud in the front, I mean, how do you know that it's, how do you tell the model that it is, how concentrated it is, if there's no data along some directions?
We don't tell it to the model at all. We, in the beginning, say we do voxelize the space, so we do discretize the entire volume. But in the beginning, we don't put a direct constraint on the amount of dust in a voxel. We only say if there's dust in one voxel, there's a higher probability of having dust in a nearby voxel. So we do have correlations that we exploit. So this is how we do the interpolation. And these correlations are actually physically motivated and driven. So we don't assume a correlation scale, but we learn that correlation scale from the data as well, because there are regions in that map where we have high resolution compared to other regions. And it's physically a reasonable assumption to make that the correlation scale of this cloud is going to be similar to the correlation scales of these clouds, simply because the environment in which they live, they don't have changed drastically yet.
But the linear correlation scales, not the angular.
The 3D correlation scale,
Cartesian.
yes.
But so when you say correlation scale, specifically is the kernel of a Gaussian process or
Yeah.
line normal process?
Yeah. Yeah.
And that kernel is isotropic, right?
Yes. Yes, I forgot to mention that in this example, we not only assume things are similarly correlated here and here, we also assume them to be isotropically correlated.
But to elaborate on what you're asking, it is true that the pixels on the plane of the sky are more well-defined than the distance
Yes.
along the line of sight, so
Yes.
you have to count for that.
So how do you see uncertainty on this?
Um,
At the end?
Yeah, could you zoom in on that or something?
I don't know.
Yeah,
I'm only using a technical screen to show.
You said uncertainty, but I don't.
It's flicker.
Yes, stuff is moving around in between samples, and the more it moves, the less certain it is.
So that's why.
It's not an artifact of the projector.
Yeah.
So estimate of uncertainty is the amount of variations in the regions.
Between the samples.
Well, we can also compute standard deviations and confidence intervals and so on.
Okay,
This is just a visual, these are 10 random realizations from the posterior,
okay.
or 8, 6, 7, 8,
Maybe
Yeah,
12.
I think that's the other side.
or 12.
It's another example of a number.
Yeah, no, absolutely. This is not our quantification of uncertainty. And also not our quantification of resolution. Maybe that's then the better. We can also, from these samples, we can ask the question as a function of scale, how certain are we about structures? And then we find that it changes as a function of distance primarily, but also as a function of location.
But then I really can't see it, because from 0 to 1,000, there's 10,000 pixels. The resolution
I
is like
really
a tenth
should,
of a part.
I really should
In
zoom,
some places.
should be able to zoom in. I'm sorry that I can't zoom in this one.
That's fair to say that that's why it looks like it's not huge.
But can I just say, someone who's looked at a lot of dust maps,
Yeah,
yeah, we're talking about, a lot of technical details here, of course, but this is astonishing.
Yes.
Like the amount of uncertainty, the fact that you're struggling to see the changes, right, means the amount of uncertainty this happens. Just impressively small, and it's really a triumph of math and statistics over the evil vagaries of astronomical. I mean, it's just,
well,
this is great.
I would say primarily the data also, right? I mean,
Well, okay, yeah.
Gaia has very much,
Gaia is not a bad data set.
but no problem. We can just go to the whole galaxy and look at gas, and then things jump around much more again.
Okay,
But
good.
that's astronomy, right? We
Yes.
just go to the next problem that we haven't solved yet. And so that's another example of applying this to a different task, which is yet again just reconstructing 3D structures of the Milky Way, but now using gas emission. And gas emission is a very different beast because we don't get as much of a direct distance tracer using only gas emission, because we see emission from emission lines, let's say the H1 or CO line emission. But we see this coming from everywhere throughout the Milky Way. And the only way so far is to link that emission to distance is by making use or assuming something about velocities. So if I see that emission line being shifted relative to the rest frame emission, and if I have an idea of how things rotate in the galaxy, and if I maybe have even individual tracers of velocity, which we get from stars and masers, as like local tracers of if this group of stars move at a certain velocity, there's the correlation with the gas moving in a similar velocity in that region. But it's a much less direct tracer, and it's much harder because, well, there are places here that have the same relative velocity to us, but are literally at the other end of the galaxy. So the degeneracies are pretty painful in this one, and we don't fully solve that yet with the data that we have. We are in the process of getting better velocity data from absorption features of starlight, and that will drastically change this. But for the time being, I just wanted to show that one as well. Because it's, on the other hand, from the inference perspective, interesting, because now we not only have to recover a density field, we also have to recover velocity fields. So now we're back in this game of we have multiple things and we measure their combination after we recover them. And despite all these drawbacks of both the data and the limits in the analysis, we overplot the density here in contours of the gas onto the dust map, while some stuff is kind of nowhere where there's no dust. There's also a lot of structure that tends to line up, is correlated with what we see in the dust map, which we trust on these scales much more in terms of distance, right? Like in the dust map, we're very confident that this structure is actually.
Where is the distance for the nearby CO ultimately coming from in that paper?
And mostly through the fact that we have the YSO clusters and the velocities, and we assume the velocities of CO and H1 should be similar to the velocities of the Y cell clusters.
But that's not all of the CO though, right?
No,
That's the problem.
Yeah.
I see.
and yeah, there's not all the CO along that emission sideline.
It's in fact probably very little of it.
Yeah,
Okay.
yes. But it is very little as sort of a distinct enough group of velocity.
You know, what's funny is this is probably less bad on large scale.
Yes, yes. That is a particularly hard one to do, but this is an interesting regime.
Well, maybe less bad off the plane a little bit, right, where you're
Yeah.
not passing through many different clouds.
Yeah, the badness, especially looking at this plot, depends a lot on where you're looking at, right? There are even regions where you have virtually no distance information because the relative velocity stays the same over most of the galaxy. So then you have no idea where to place your emission. That's sort of the most bad place to look at.
I'm sorry I haven't read the paper yet, I just downloaded, but is there any combination where the dust is actually used as a prior on the actual CO map instead of the YSL?
Not yet.
Okay.
But
We'll talk about that.
we're in the process of that. And diffuse interstellar bands, I want to really very much add to that, right?
That would be a great idea.
I've heard something about that happening.
That's a different talk though. But let me just finish with another, just to show that this, even though I spent most of my time with tomography over the last year or two or so. This is also the same concepts and the same techniques are being used in different areas and explored in different areas as well. And this is doing reconstructions of Chandra data. Okay, the data we can't see much. But this is sort of doing a multi-frequency imaging reconstruction using X-ray data. And here the idea is again a bit simpler because you only have sort of one diffuse component, but then there are also point sources in that field. So you have to again make a decision where to put your flux that you observe. Is it more a point source or more diffuse emission? And rather than doing this sequentially, we do a joint analysis of both of it together. So you basically get a whole posterior distribution of point source and diffuse flux. And that helps to cure some of these aspects. And that gives you then the diffuse one, which is mostly removed of point sources modulo places where the point spread function was mismodeled to talk to the people that have fun with that. And just as a last gimmick, one of our students has asked the question, well, now that we have something which is structurally, okay, it's really, it's too bright. I'll send around the slides later and then.
It looks really good here.
Yeah, something that the student has looked at, given that supernova remnants are, let's say, we can have a decent prior on things being somewhat spherical. And we asked the question, what if we make a 3D prior that promotes things that are spherical as more likely from the prior? And say, if we only have looked at this from one angle, how would the full 3D thing look like? And from one angle, it looks like the image, because that's where the data is. From the other angles, you basically get like warping through posterior samples of all the shells that are consistent with this 2D image. And the assumption that you made on things are primarily distributed at the, like there's a higher probability to have things at similar radii. That's sort of the extra prior that went into this. Yeah.
But viewing it from one angle is fairly weak information, which is why the posteriors are treated a lot. But I'll bet if you had even two views of it, you would constrain it pretty well.
Or velocity or time.
Or something
Right.
else.
And there's so much data on this one, right? Just throwing it out there. Yeah. Yes. I think we're slowly at the hour, so let me conclude with this one yet again. An interesting one from a separating components perspective, strong lensing with JWST. this is again interesting from the point of view that you have a background galaxy that you don't know how flux looks like. You have a foreground galaxy that has its own light coming in the visible, but then also has a dark matter profile, which lenses the background light, and you observe its combination. Now you again ask the question, can we jointly recover the source distributed light and the lens light and the lens dark matter profile from the images? And in particular, people are interested in, so this is on real data. People are particularly interested in what do we do with substructure? This is simulated things with substructure. And the point is, if we model things in this random function space, substructure or no substructure is not a different model. It's just the Gaussian or Log-Noble process that go into these profile functions. They then just have an excess somewhere. So mapping this out can be helpful to get a better handle on this. And also people are working on that.
So one of the issues that's come up because of generosity is MOND, modified Newtonian dynamics.
Yeah.
Is it, do you think this sort of thing can be used to either deprecate or?
I don't know.
Bond cannot be killed.
I really don't know.
I mean, if you
Enough
can
about
change
this.
the dark matter distribution, or
Yeah.
effectively remove dark matter with MOND, do you get back the right, I mean, can it be fit? Do you get a good?
I don't know. I don't know. Because. Yeah, I really don't, and I don't know if we can help with that because we're trying to decompose the background structure and the foreground structure simultaneously. So you have this degeneracy if you modify the way that the foreground structure affects the background structure. You could also change the background structure. And I don't know enough, or that being said, I don't know really anything about how MOND modifies that relation to say whether this can be.
I mean, if there's no dark matter, then there has to be a change in the lensing light, right? So,
Yeah, but at the same time, you could then make your source less compact or like deform it, so. I don't know.
It would give you at least testable predictions, you know, if as you say, it's got to be less compact or more compact.
Yeah.
Compared to other wavelength data.
Yes.
We could also.
So a quick Googling of that question says Milgram's original MOND theory does not explain lensing.
Doesn't it?
Okay.
So the original MOND theory by Milgram does not explain lensing,
Right.
or at least
Oh,
not
yeah.
in any
No.
satisfactory way, but there are these kind of relativistic extensions to MOND that people have worked on more recently that claim to kind of mimic the same sort of lensing signals. So I mean, that's the problem, is you take MOND and make it more and more like GR, it explains more and more things.
Wow, good idea.
So that's why I say MOND cannot be killed, because it keeps morphing into things that explain this or that other.
Yes. On that note, let me wrap up and let me conclude just with a brief summary of sort of where we at with this, or where we have stopped a couple of years ago and then started doing physics again. No, I really wish I would have more time to work on this because this is fun as well, right? It's a lot of fun. Anyway, okay, so pros, we can, at least in the unimodal setting, go towards non-Gaussian approximations, and we get a bit of a feeling for how good we can do there. What's really helpful for us was this implicit representation of things, that the number of VI parameters are the number of parameters of your problem. To be fair, you do have to carry around your likelihood function. So that contains the data set, for example, so you do have to have that around, which is also one of the limitations, that naively it will run on the full data space and parameter space. So there's getting a mini batched version or like a stochastic extension of this work is difficult. because in order to construct that coordinate system, you need to look at all your data. It's or compress it into a different set of parameters, which then you have to get a reason for why you do that. So that's work to do. There remains a zero residual error, even if we run it infinitely long. That's sort of the nice thing where other techniques with more expressive capabilities and or just full posterior sampling in this limited of infinite compute, they tend to converge to the full posterior. Because we do variational approximation, we stop at some point, and that error is something we don't do anything on top of that remains. Something that I haven't talked about much is how to actually get to the minimum. And what's kind of nice is if you already have this metric around, it's a proxy for curvature. So it also gives you somewhat a way to do proximal second order steps kind of for free, because you have to have it anywhere around for your sampling. The approximate posterior expression is analytics. So we can compute its normalization. It's a bit costly, but we can get basically the evidence of this approximation. And while it's not the evidence of the actual posterior, if we believe the approximation, it's something useful for us to work with. And yes, it's very much in the space of techniques, one that requires explicit likelihoods and like gradients and so on thereof. So unless there's an other way to implicitly construct the value gradient and metric, or the matrix vector product of the metric to be precise, that's the only thing we actually use. Yeah, this is very much in the space of explicit likelihood methods. And yeah, with that, let me leave you with the obligatory software slide. This is all public and open source, and you can play around with it. And there's spin-off libraries for the examples that I've showed you, or people for radiant photometry and for imaging. We don't have a dust mapping library yet, right? Just now that I mention it. We should. Yes, and it's all in the JAX ecosystem. So if you want to interface with either the models or the sampler or any subset of things with your favorite JAX work, you can just do that. Thanks for your time.
This is something that I've been working on with Matthew Callahan, who is at Cambridge.
Yeah.
Is looking at that linear mapping and thinking about models that will make it more flexible. In the
Yes.
sense that we're handling multimodals. And what Matthew's really done a lot of work on is normalizing flows.
Yes.
To do this mapping. And they seem to be really well. There's some caveats to that. Have you looked at normalizing flows?
Yeah, we have looked at normalizing flows. And I think if you can afford the parameters, they end up being more expressive, right? The training and normalizing flow is significantly more expensive than running this once. So it's also a bit of a question of do you need a sampler?
It's accuracy versus the speed. Yeah.
Exactly.
Yeah.
And it's also a bit, I think, normalizing flows, or like in general, diffusion flow models are very cool if you start doing simulation-based inference. If you want to solve the same problem many times, I think there's a really cool, we're sort of in the business of, we have this one big problem that we ideally want to solve only once. And it's so big that anything better than nothing is sort of, but yes, I think the main constraint for us with normalizing flows is the number of parameters. That's kind of ends up being the bottleneck.
I mean, we started looking at score-based diffusion models.
Yeah.
To do some of this, and there you get, because normalizing flows, we're finding that the amplitudes, it doesn't do well with the amplitudes of the modes in the posterior. But the diffusion models do really well.
They do
there.
really well there, yeah.
But the training is really brutal there. You take a huge hit with the training, but they're very, very accurate, so.
Yeah, so what I've started looking at that I'm very curious about is see if we can combine more of this with diffusion and flow-based models, because what diffusion and flow is kind of solved is this condition number problem, that by doing this sort of tempering what people tried to do years ago, but it never really worked, but doing it in a way that's good by breaking up your KL into these time chunks. you kind of get much better condition numbers and you can flow into the modes. Like that's what we kind of try to make use here a lot of is this. We have an explicit likelihood and we have its like gradients and curvature. We make use of this very explicitly. And we're working on ways of, can we use that information to build diffusion models for more efficiently? Because they are very sample hungry and you have to run your thing many times. But if you get a gradient of the curvature for every one for free, you get much more information.
Jeff Scarborough has a
Yes.
question.
Yes, thanks. I apologized. I tuned in late and probably you discussed this. Your abstract talks about situations that implies the kind of situation I'm interested in is where you have a model that has some parameters in it, but it fits the data exactly. So you're trying to optimize the model and estimate the parameters, not by any consideration of the residuals, but by some a metric of some property of the model. Is that something that this approach can handle? It's sort of an ill-posed. Well, I think of it as a sort of overdetermined, slightly ill-posed problem or something like that. But I mean, maybe I'm not being too coherent, but
if I understand your question correctly, you're asking in the space of problems where where your solution is overdetermined or fully determined and finding the solution in that problem setup, right?
I think that's what it is.
We have not worked on this, and this as of now. So the design idea here is we work in under constrained problem spaces. So we have more degrees of freedom, or we have noise in our measurements such that the problems are under constraint, and we try to solve those with these techniques. I don't think it's directly applicable, no.
Okay, so because the methods are sort of focused directly on the residuals between the model and the data, is that the underlying reason, or?
Because the methods are focused on techniques where you have an explicit likelihood or an explicit representation of your posterior that you can evaluate. And if your model is over constrained, then that explicit form is always a delta function. It's either true or false. Whereas we work in the space of models where you can make use of gradients and curvature of that. And so if your gradient is always 0 or infinite, this technique doesn't really apply.
Okay,
That...
Thank you.
I have a question. I don't know if it's astronomical method about CO. So
Yeah.
Is it possible to determine whether you have a CO outflow from the galaxy? Maybe that's already known.
Tom Dame, a long time ago, did an extra survey with the telescope with the CFA of stuff that would be called high altitude. And he didn't find evidence for that, but whether if you looked longer, I don't know. Anybody else have an opinion?
I was just thinking when I saw these velocity maps and some. It's not the question you're asking.
This is not the LB plot, this is the LV plot. I don't have the LB, I thought I had the LB plot here, but if one looks at the LB plot, at least of the Dame survey, I think there are a few places targeted high where there's not really nothing.
Right. So far, nothing, but it's a very small telescope.
Yeah.
Oh, yeah. Just the question for the galaxy.
I don't know. I mean, there's people looking in the streams and things like that, but that's not the same as what you're asking.
No, I'm just.
So I think the answer is we don't know, but the limits are pretty low.
Is that a beer question?
I don't think so, not with the CO.
No, with the CO, yeah, that was like general.
Just the molecular outflow, so.
I mean,
CO is.
CO is it's a nice molecule, relatively stable molecules go, but it's still fragile, right? If you like, if something blows up to drive something up a chimney or something, you know, the shock. Take it apart.
No, there's still, you know, 200, 250 parsecs off the plane, but not a kiloparsec off the plane, like nobody's ever seen.
In our.
In our,
Yeah.
And question about, so you talked about millions of dimensions in the problem. What's the smallest that you think is worthwhile trying? You know, is 10,000 good? Is it worthwhile trying to do this sort of thing?
So I can tell you for this example, for the 1D example that I was showing. Sorry for jumping around. This was, I think, 512.
Okay, small.
So I would just say in that regime, Hamiltonian Monte Carlo, that sort of has the same requirements, as in you need an explicit likelihood and a gradient, and the metric makes your Hamiltonian Monte Carlo maybe more efficient, but it's not even a necessity. Works so well that and converges to the true answer that I would recommend to use that. I think if you can afford something that answers your question less ambiguous, there's still multimodality where I think only you really want to go down to it. There's nested sampling as kind of the old, quote unquote, old technique. Yeah, or if you really have enough time to sample and train a flow model unambiguously. I think that the tricky bit is to make sure that you haven't missed something in the training, which is not an easy question. But then they end up being significantly more efficient afterwards and more accurate. Yeah.
Solar data, have you tried this on solar data? We have a lot of, you know, structure.
Not on solar. Well, we've validated on solar data, but there's a project in helioseismology together with Earl Bellinger at Yale University, who's been applying this to oscillation modes of other stars. And then the sun has so many modes that it's a very good validation bet, but it's more used as a validation of the techniques. But no, I think there's something that comes up repeatedly, and in the former group of Thorsten Ensinger was working in, it's a recurring theme that someone says every once in a while we should look at the sun.
I mean, you got this magnetic fields there, you have eruptions, like the active regions.
Yeah, I think the surface of the sun, mapping this out with like this kind of spatial temporal correlated techniques. I don't know what's the state of the literature there. Maybe people do this already.
Well, I don't think the global sun, because it's hard, right?
Well, the problem with the sun is that, well, for one thing, there's too much data.
Yeah, that's what I mean.
Yeah.
Yeah, so
and
when
which,
you look at the whole sun, right, you got these regions. and
yeah, so you gotta be very careful with what's the question you're asking, right? So what is it that you're trying to solve?
Yeah.
And some of the popular things might be, when does a flare go off, right? When, you know, what's the thing that differentiates CME coming out versus no CME, that sort of thing. So if there is a way to model that, or at least predict that, that's useful. But then you're faced with the fact that your models are not good enough to do that.
Yeah.
So there has to be an empirical model of some sort. So if this method can do that, you know, effectively find correlation. Actually, maybe that's a good way to look at it. If you can find the right correlations, that's useful to know.
I mean, across the whole sun, you can imagine that you have the sort of moving sun,
Yeah,
and in time, and once in a while you get an eruption, and if you have enough data, maybe there is some correlations which lead to those eruptions. I mean, we don't know.
And you have to work on multiple scales.
Yeah.
This is something which we have worked on a lot to make. Yeah, I think in terms of looking at residual to stellar models as like, seeing if we can have a more structured residual distribution. That sounds cool.
So no other questions, we are close to 1:30, so thank you again.
Hi, everyone on Zoom.
See everyone here. Are you doing?
You know, I put it on your calendar, but you know, it's not there.
Everyone.
You put a meeting in my.